So we're going to use Kirchhoff's principles in a couple of applications here. First of all, we're going to find the voltage difference between any 2 points in a circuit. Now, a couple of things to keep in mind. We'll use plus to stand for higher voltage or higher potential, and minus for lower. So for instance, on a cell, this terminal here, the negative terminal, will automatically be lower potential. So this is a 10 volt difference between these two. This is the lower side, this is the higher side. Now current, just like water in nature, flows downhill from positive to negative. So the fact that there's 1 amp of current flow in this direction through this resistor means this end is uphill and this is down. We could follow that 1 amp of current around and we can see that because the current must flow downhill, this is higher, this is lower, this is higher here, this is lower. On this cell, this is the low end, this is the high end, based on the diagram of the cell, based on the direction of this current, and given that it flows downhill, that must be positive and that must be negative. So as we've been saying, plus to minus represents a downhill or a loss of height, a loss of energy, and minus to plus means uphill. So if we wanted to find the voltage difference between the points A and B, first we would label the cells and resistors, which we've done. Then we will walk through the circuit and just keep track of the voltage changes. So let's do that now. Let's start at A, and then if we walk this way towards B, the first thing that will happen is we will gain 10 volts. Then there will be a drop across this resistor, and the drop is I times R. Now the current, as we said previously, will be 1 amp, and the resistance there is 1 ohm. Then there's another drop, now 1 amp times 9 ohms. Then proceeding still towards the point B, here we have a gain of 8 volts, going from minus to plus, that's going uphill. And then we go downhill here, so that's a loss, it's 1 ohm times 5 amps of current, and then we arrive at the point B. So adding those all up, I get VA, so this is 18 minus 15, that's 3. Okay, I'm not sure why I hadn't noticed that ever before, but there's a mistake there. This can't be a 1 ohm resistor, it has to be 0.6, for reasons that will become clear shortly. So then there's a drop of 5 amps times 0.6 ohms right there. And so that's 18 minus 9, 1, and 3. It's actually 5 equals VB. So that tells us that the point B is at higher voltage or potential than the point A by 5. Now, we have to actually get the same answer no matter which way we go. So if we proceed from A to B directly across this way, we have to get the same answer. Now we're going from lower to higher, so that's a gain of 5 ohms times 1 amp. And so we see again that B is just 5 volts higher in potential than the point A was. So you have to get the same answer no matter which way you go. Here's another example. We want to find the potential difference between the points A and D, given there's 1.7 amps of current flowing in this direction. So why don't you pause the video, try this one, and then turn it back on to compare answers. So pause it now, give this one a try. Okay, so the first thing you should have done was label this. This is the lower energy end of the cell, this is the higher end, minus and positive. Current flows downhill, so this is plus, this is minus, this is plus, this is minus. So if we start off at the point A, we're going to gain in this resistor I times R. Then walking towards D, there's another gain. We're going uphill here, I times R. Then there's a drop here of 45 because we're going from higher to lower, and then we end up at the point D. So if you add that up, that's, let's see, 17 times 4, that's 68. That's another 1.7. and then there's a drop of 45 there. So 24.7. So this tells us that the point D is 24.7 volts higher than the point A. We can represent that graphically here. So here we start off at the point A with a certain unknown potential. And then there's a gain here of 24.7 volts. So the potential doesn't really change very much in the wire, but in the resistor it changes. So this is up by, how much was that? 68 volts. Then again, there's not much change in the wire, but then in this 1 ohm resistor you gain another 1.7. So we're now 69.7 volts above where we started. And then there's a drop of 45 here. And so we're back down here, 45 volts in the cell, and then this is the voltage at the point D. I didn't start this one off correctly. That should have started down at this point right here at the point A. So there we are right there. So as we go, there's not much, oh my goodness. So right there, there's not much change. Then as from one side of the resistor to the other, there's an increase of 68 volts. Let's clean that up. This is now the graph we wanted. And again, there's not much change in the wire. And then there's another 1.7 increase in the resistor. So you're now 69.7 above where you were, voltage A. Then there's a drop of 45, and you end up at voltage D, which is 24.7. That's 24.7 volts above where you started. Okay, so hopefully that's the answer you got. Let's now look at a similar problem, the problem of calculating the terminal voltage of a cell. So a cell we can imagine, or we can represent electrically as being an EMF and a little bit of resistance. This is called the internal resistance of the cell. And this is the the internal voltage, or the chemistry voltage, or the EMF. Now the actual terminal voltage you get out of the cell depends on both of those in the following way. If there's a current flow I through this cell, then the difference across the two ends is going to depend on the chemistry voltage E, but also on the drop, the voltage drop across this internal resistance. So let's do a little derivation. Here we have the cell supplying current I. These two dots here are meant to represent the ends of our Duracell. So there's a Duracell here, and this is the minus, this is the plus, so this would be the end with the bump on it. So how much voltage do we get out of our Duracell? So if we were to call this point X and this point Y, then starting at the point Y, or starting at the point X, I guess it doesn't really matter, we would gain our chemistry voltage E. Then we would have a drop because current flows downhill. It flows from positive to negative. There'd be a drop of IR, and then we would arrive at the point Y. So solving for Vy minus Vx, which is the difference between the two ends of the dry cell, you get E, the chemistry voltage, minus IR. This is called the terminal voltage of the dry cell. So here's a numerical example. Here's our Duracell. There's 2 ohms of internal resistance. It's hooked up to a 30 ohm load. Well, internal resistances, in this case it's in series, so we do treat it just the same as another resistor. So there's 32 ohms of total resistance. So we find the current, 20 volts over 32 ohms. So let's see what that is. So is that right? Yes, I guess that is right. Silly me. So that's 0.625 amperes of current. And then we can find the terminal voltage. There's going to be the chemistry voltage minus the drop across the internal resistance. So it's 20 minus 2 times 0.625, and that's 18.8 volts of terminal voltage. That's the difference between those 2 points. So this relationship that we've derived here is a general relationship that will apply when the cell is supplying energy to the circuit. If, on the other hand, the cell is being charged, well, the way that we charge a cell is by running current back through it using a battery charger. So now the current's flowing in the other direction, and current flowing downhill, those will be the energy labels for the resistor, and these are the energy labels for the cell. So now, once again, if we consider the point X and Y, X being at this end and Y being up here, so walking from X to Y, you would gain chemistry voltage I, you would gain energy across the internal resistance, and then arrive at the other terminal. So if you find the voltage difference across the two terminals, you get chemistry voltage plus IR. So here, again, those resistors are just in series, so it's 5 plus 5 plus 1. That's 11 ohms of net resistance. Now, notice the cells are opposite to each other, as indeed they need to be, so that the charger can actually push current back through this 9-volt cell that we're charging. The net volts, because they're opposite, we will subtract and get 21 net volts. So our current will just be V over R is 21 volts over 11 ohms. And that's 1.91 amps. And so now we can find the terminal voltage on the cell that's being charged. Now there's a gain of energy across the internal resistance. So it's 9 plus 1.91 times 1 ohm of internal resistance. That's 10.91 volts. Okay, and so that then concludes our brief presentation on finding potential difference and on finding terminal voltage.